Howdy class, this is a continuation of our lecture from class today. We started the test review for test number 2. That would be, the test review is homework number 13, and we did problems 1 through 6 together, very detailed. It took the whole class period, and I'm going to pick up on number 7. All right, so if you just watch the rest of the video, you'll see the rest of homework 13 worked out. Okay, so picking up where we left off, we can look at number 7. We have some missing side lengths within a sort of dissected rectangle here. We have A, B, C, and D that we need to find before we do anything else. I gave a little hint at the bottom here that says to go in alphabetical order. Okay, so first we will find A, then B, then C, then D. On your test, this asks you to go a little bit further, and I'm going to go into detail on this so that you can get full marks on your test. The first thing I'd like you to realize is that this is a problem where we take a golden rectangle, we chop off a square, we look at the rectangle that remains, we chop off the largest possible square again, and we're left with a rectangle BD, all right, with side lengths B and D. That's what we're doing here. So what we can call upon is the definition of a square, okay? Yes, it has 4 right angles, but the big deal here is that it has 4 sides that are the same. So A, 24, this blank side and this long blank side here all have the same measurement. So A must be equal to 24 because it's the side of a square with side lengths 24. So we're going to continue on in alphabetical order doing sort of a thought process like that or similar to that as we go. Once you have A, you can start to figure out what B is. And the way we're going to approach this is by considering the fact that in a rectangle, opposite sides have the same length. So let's think about this long side here, 12 plus 12 root 5, having the same length as the entire bottom of this rectangle. Okay, so the top of the rectangle is 12 plus 12 root 5. The bottom rectangle is made up of 2 measurements. The bottom of the rectangle is made up of a measurement of A, which we now know is a length of 24, and another length that we have called B, but we don't know how long it is. So what we need to do is take the entire 12 plus 12 root 5 and subtract off or chop off 24 units of that length. We're going to remove 24 units of that length. That's going to leave us with the length of B. So we're going to do long side minus A, long side minus A. That's going to give us the length of B. Okay, so you can see just by substitution we can determine the length of B. What we're going to do is the long side minus A is going to give us the length of B. That's 12 plus 12 root 5 minus 24. Now I've got some like terms here. That would be just the 12, and the negative 24. Those are numbers I can add together. Okay, 12 minus 24 is going to yield negative 12. That number that has the square root of 5 is not a like term to these constants, okay? I can't add the 12 root 5 to the other negative 12, okay? So 12 square root of 5 is irrational. It cannot be added to a rational number like that, okay? So I cannot simplify B any further. You could approximate it using a decimal for some partial credit, okay, but that's not going to get you full credit here. In fact, it'll make the rest of your answers close but wrong because we're going to rely on B to calculate the rest of the answers here. we can start to mark off all of the measurements which have the same length as B. We're going to use these shapes and their properties to our advantage. I found out that B, the length down here, is equal to negative 12 plus 12 root 5. All right, negative 12 plus 12 root 5. This BD rectangle has opposite sides equal, so this length here is negative 12 plus 12 root 5. And in the top, if you take 12 plus 12 root 5 and you chop off A, you're left with B, which is negative 12 plus 12 root 5. Okay, we're just labeling the things that we know. Every side that has a purple highlighted edge has the same length as B. Okay, and we're going to work in through those. Now, if you recall, we started with a golden rectangle. We chopped off the largest possible square. So we're left with this golden rectangle here. This is a very small, or a much smaller golden rectangle. Well, what we're doing again is we're chopping off a square that has side length C. That's the largest possible square that we can sort of chop out of this figure. So I know that this is a square. Okay, so in identifying that this is a square, we're going to identify that all four sides must be equal. Therefore, C also is negative 12 plus 12 root 5. So the way that you can remember this is that A is equal to the short side. That's what's occurred here. And C is equal to B. They're always equal here, okay? Whenever we're working this kind of problem where we're chopping off these squares and going in alphabetical order. All right, we found A, we found B, we know C equals B, so we also found C. The last side length that's missing here is D. The way we're going to find that is the same sort of reasoning that we've been using all along, especially to find B. We know, based on the computations that we've done, okay, we know, actually not even the computations, just the reasoning, that this whole length here that I'm highlighting, okay, I'm sort of coloring in here, this whole length is 24. We know based on our work with B and C that this second length here, I'll do this in green, but it's already highlighted in purple, is equal to C, which is negative 12, and I'll write that in, negative 12 plus 12 square root of 5. Okay, I have all of those values. So we could do a sort of drawing where we remove these pieces to the side and just consider them as independent lengths from the figure. I have a whole length, which is 24. Okay, I have a partial length of that 24, which is how long? It is negative 12 plus 12 root 5 units. Okay, it has a length of C. The leftover bit that I have that finishes off the length of 24 has a length of D. That's this length here, right? Because opposite sides of a rectangle are equal. So those two sides that I've marked in green horizontally and that have already been marked in orange vertically have the same length. This is a rectangle, so opposite sides are equal. So if I can find the length here, then I am also finding D at the same time. So the way we calculate that, similar to B, is we do 24, the whole length, 24, subtract off negative 12 plus 12 root 5. We're going to subtract that off. That is going to give us D. So let's look at that work. We've got, it's kind of going to move some of my drawings whenever I move this shape around, but we really just want to look at the math on the right-hand side anyway. D will be equal to 24 minus the length of C. That was the negative 12 plus 12 root 5. We have to be very careful that we write C in parentheses because we're subtracting two terms. So I need to subtract negative 12 and I need to subtract positive 12 root 5. Okay, so some of you might be wondering how this negative gets distributed. We're subtracting negative 12, subtracting negative 12. Subtracting a negative is the same thing as adding a positive. So that's how this became positive 12 down here in the next step. It's not enough just to do it to the first term. We are subtracting both of these quantities. So I'm also subtracting positive 12 root 5. Subtracting positive 12 root 5, well, that's just subtracting 12 root 5. Okay, and that's how it's become negative 12 root 5 in the next step. Let's keep going here. See what we can do here. Oh, it's kind of moving everything around now. Luckily, we're in the last step, so it'll be okay. We're now looking at finishing solving for D using the values that we already have there. Sorry, things are getting a little wonky here. We can combine like terms just like we did before. I have a 24 and a positive 12. Those are going to add together to give me a 36. Now I have an irrational number here. 12 root 5 is irrational, so I can't add it to those rational numbers. It's negative 12 root 5, so I'm subtracting 12 root 5 from 36. This is as precise as you can possibly be. You now have all of the lengths of A, B, C, and D. Your test is going to take it a little bit further than the review. It's nothing you haven't done before, but it is going to test whether you know how to check if a rectangle is golden. So you have to check whether or not the resulting rectangle with lengths B and D is golden. Is this a golden rectangle? Okay, remember how we do that. What we have to do is divide the longest side of this rectangle by the shortest side. If you do the math and simplify that division problem and you wind up with exactly the golden ratio, not a decimal approximation, exactly the golden ratio, then you have a golden rectangle. So we have to go through all of those steps. All right, remember that B was equal to negative 12 plus 12 root 5. And D was equal to 36 minus 12 root 5. Okay, those are the two lengths that we have here. You could type those into your calculator to see which one was bigger, which one is smaller. Okay, but based on how we got this rectangle, we know B will be larger because we started with a giant golden rectangle, chopped off the largest possible square. Here was B. Then we looked at this remaining golden rectangle. Here was C and D. We chopped off the largest possible square here. So we know that B will be the long side here. Okay, so what we do is we just do a direct substitution. We do negative 12 plus 12 root 5 as the long side and divide it by the short side, which has a length of 36 minus 12 root 5. Okay, just like in the previous problem from the review that we worked together, we need to rationalize the denominator. We write that numerator here, 12 plus 12 root 5. Rewrite the denominator just as it was. And to rationalize that denominator, we are going to be multiplying numerator and denominator by 36 plus 12 root 5. Okay, we are changing the sign of the denominator here, and that's going to help rationalize the denominator. Okay, let's keep going. Step by step here, we need to multiply across the numerator these two terms by these two terms. Then we'll do the denominator, these two terms by these two terms. Okay, I'm going to try to use color to guide our process and to kind of structure where I'm getting the different terms from. Okay, what I need to do is double distribution, or FOIL if you learned it a long time ago. We're doing negative 12 times 36 and negative 12 times 12 root 5. Okay, so we've got negative 12 times 36 and negative 12 times 12 square root 5. All right, so you can see the green negative 12 is coming from the numerator, this first set here. Then the white terms are coming from the second set of numbers in the numerator here. If we keep going, I'll see if I can get another color out here, like a yellow. I need to take the second number from my first set of parentheses, 12 root 5, and multiply it by both terms in the second set of parentheses. So that's going to be plus 12 root 5 times 36 plus 12 root 5, that's from the first set of numbers in the numerator, times 12 root 5 from the second set of numbers in the parentheses here. So you can use those colors. All of the white numbers are coming from the second set of numbers in the numerator. The green negative 12, that's coming from here. And the yellow negative 12, that's coming, I'm sorry, the negative 12 root 5 is coming from here. So you can follow along that process. Let's do the denominator. All right, let's do this all in one. So let's go back to green. I'm doing 36 times 36 and 36 times 12 root 5. So I've got 36 times 36 plus 36 times 12 root 5. All right, and we're going to use yellow for this one. Negative 12 root 5 also has to be multiplied by both of these terms, 36 and 12 root 5. So let's go ahead and do that. Let's follow along here. I've got negative 12 square root of 5 being multiplied by 36. Lastly, I'm taking negative 12 root 5 and multiplying it by positive 12 root 5. Times positive 12 root 5. Okay, so our whole goal in the next step is just to simplify each one of those terms into something a little bit easier to digest. Okay, so my next step, I'm going to start on the next line, equals, now we've got a ratio here, fraction. We're going to do negative 12 times 36, negative 12 times 36 yields negative 432. Then I have, I'm going to use some colors here, maybe it'll help us map even further. Negative 12 times 12 root 5. I can multiply numbers outside of the parentheses, outside of the radical together. Separately, I can multiply numbers under the radical together, and they stay under the radical, okay? I only have numbers outside of the radical that need to be multiplied together here. So I'm doing negative 12 times 12 is negative 144. And the square root of 5, it didn't have any other square root. It didn't have any other radical numbers to be multiplying together. So it's just by itself, square root of 5 is coming along. Okay, let's keep going down the line here. I've got 12 root 5 and 36 being multiplied together. So I'm doing 12 times 36, the two numbers that are outside of the parenthesis, outside of the radical, which is 432. There's only one number inside of the radical, so we drag that along, square root of 5. I'll get one more color here. See if this will work if it's not too bright. I've got 12 root 5 times 12 root 5. Well, I multiply the numbers outside of the radical, I get 12 times 12, that's 144. Under the radical, I finally have something interesting going on. Under the radical, I have a 5, and under this radical, I have a 5. So I need to do 5 times 5 under the radical, which is radical 25. Okay, square root of 25. Let's do the denominator. We're just going to go step by step on these. Right, so first we're going to do 36 times 36, which is 1296, and you can just get that using your calculator. Maybe you're really good with your squares and you know all of them. Then we need to do 36 times 12 root 5. So the numbers outside the radical are 36 and 12, so I'll multiply those together to get 432. That number keeps showing up. There's only one number in a radical, it's at 5, so that radical will only have that 5 inside. Keep looking here. We're going to do negative 12 times 36. That's negative 432. It also has a single square root of 5 attached to it, multiplied there. Okay. Then lastly, the last numbers that we're multiplying together, I have negative 12 times 12. Those are the numbers outside the radical. The numbers inside of the radical are square root of 5 and square root of 5. Okay, so negative 12 times negative 12 is negative 12 times positive 12 is negative 144. And square root of 5 times square root of 5 is square root of 25. We multiply those numbers under the radical together as well. We're going to keep reducing in the numerator. All right. We need to acknowledge that the square root of 25, that can be reduced. The square root of 25 is just 5. All right, the square root of 25 is just 5. So in my next step, I'm just going to start writing some things that have been simplified. I've got negative 432. I'm doing, I have a negative 144 square root of 5. I have a positive 432 square root of 5. Right. And I have 144 times 5. That 5 comes out of the radical when we simplified the square root of 25. So I can do 144 times 5, which is 470. And since that doesn't have a radical on it, I want to move it to the front. I want to put it with the other numbers that don't have any radicals. So you can see negative 432 and 720, those don't have radicals. Negative 144 root 5 and 432 root 5, those have radicals. So I wrote them just adjacent to each other. All right, we need to also do the denominator. So similar to the top, I want to look at the fact that the square root of 25 is 5, okay? And I want to simplify this as much as possible. So I'm going to be multiplying 144 times 5. That's going to come in just a moment. Now, let's pay special attention to the fact that I have positive 432 root 5 and minus 432 root 5. The positive and negative, they cancel each other out. This becomes 0. It's like adding nothing. If I give you 432 of something and I take 432 of something away from you, well then you don't have any left. I didn't give you anything. I haven't changed anything. So I just have a big old 0 there. So what's left in the denominator here? All right. We have 1296, just reading from left to right. 1296 plus 0. I'm not even going to bother writing that. All right, plus 0. And then I need to subtract off 144 times 5. I'm subtracting off 720. 720. Let's continue simplifying. Okay, we can get there. We just have to continue simplifying. So we subtract any like terms. All right, rational numbers can be subtracted. Irrational numbers can be added or subtracted together. We're going to do that now. So starting in the numerator, as usual, we'll do negative 432 plus 720 to get 288. That's a positive 288. We're doing negative 144 plus 432. Again, that's positive 288. And what I'm doing is I'm counting up the number of square root of 5 that I have. So I have 432 square roots of 5, and I give away 144 square roots of 5, that leaves me with 288 square roots of 5. Okay, that's how I like to think about it. Let's look at the denominator. 1296 minus 720. That's 576. Now we are 2 steps away from the finish line here. All right, so normally I would clear the screen and try to make it look a lot better. Maybe I can move everything up a little bit. Wow, magic. All right, let's finish this problem off here. I want to start simplifying. I'm going to go to the next line, sort of in the middle here, so I have enough room to finish. You can see that I have 288 plus 288 plus, times the square root of 5. Well, I need to factor out that common term, that 288. I'm factoring it out. Okay, 1 plus the square root of 5 times 288. These two numerators are identical. Okay, well, they're equal in value, but you can see I've made a change in their representation, okay, for 576. Now, let's take 288, divide it by 576, and see if that gives us something good here, okay? And it does. It just so happens that 288 is half of 576. So look what we wind up with. 1 times 1 plus the square root of 5 divided by 2. This is the golden ratio. Therefore, the rectangle that has side lengths B and D from the original problem is in fact golden, and this is how you show it. It's a lot of work. Okay, make sure that you write down all your steps. You have to show work on these problems. This one doesn't feel like it needs too much explanation. You should be able to identify these figures. I'm not going to give them to you. What I will say is that if you're struggling to identify the shape, what you need to do is identify what polygon makes up this shape. You can't see that color there. So identify the polygon. Okay, is it a triangle? Is it a square? Or is the polygon that makes up the faces of the solid a pentagon, regular pentagon? Okay, once you figure that out, you're going to say how many polygons meet at a vertex. You can look at any vertex and see that here, for instance, I have 1, 2, 3 squares meeting at a vertex. So you can use your reference charts to figure out how many, which Platonic solid that is. For instance, here I have 1, 2, 3, 4, 5 triangles meeting at a vertex. So you need to be able to figure out what shape that is. This problem was also taken, this number 9, it's also taken directly from one of the homeworks and one of the lectures that were already given on section 4.5. 4.5 was Platonic solids. 4.5, sheesh, I can't get this marker to work. 4.5 was Platonic solids. So you can go and view that lecture or do those homeworks in order to, homework 12, in order to get these values. Once you fill in your table, it'll be really easy for you to apply Euler's characteristic because you have your vertices for V, edges for E, and F for faces in this formula. Okay, I will do one of them, but I know you guys can do this on your own, or I know y'all can do this on your own. Okay, so for the tetrahedron, in each of these cases though, we're doing V minus E plus F with a little substitution here. I'm going to move down this rectangle so we can view V, E, and F. Okay, so we're gonna do 4 vertices minus 6 edges and add 4 faces back. All right, so I'm doing 4 minus 6 is -2. and -2 plus 4 is +2. So this is the first one that you're going to get. After you compute this for each of the remaining 4 Platonic solids, you need to explain what pattern you see. There is a pattern that comes out of here, and you need to explain that pattern and show your work. With this problem, we are filling in yet another table about the Platonic solids. Okay, this time we're going to be talking about internal angles of the polygons that make up all of these different Platonic solids. If you remember, we have triangles which have a 60-degree internal angle. Let me use a better color here, sorry about that. So we have the triangle, the equilateral triangle has a 60-degree angle. The square has a 90-degree internal angle. Each one of the angles in a square is right. In a pentagon, the internal angle is 108 degrees. And in the hexagon, we have a measurement of 120 degrees per angle. Okay, so here's what we're going to do now. This is setting us up for a nice proof by exhaustion, okay, that we covered in class. We're going to use this table to do our computations ahead of time to make it very easy for our proof to kind of just fall into place. Okay, so here we go. When 3 triangles meet at a vertex, we add up the internal angles. That's 60 degrees times 3 triangles that meet there, and that gives us 180 degrees when 3 triangles meet at a vertex. I don't even need for us to think beyond 2 dimensions right now. If you lay 3 triangles down together, okay, on a flat surface, and you just add up those angles, so here's a triangle, here's a, whoops, okay, I'm not an artist here, but we're going to try to say these are lying flat on a sheet. I'm adding this angle, and this angle. We're adding up 60 degrees. Now, when we go to make this 3-dimensional, we would glue a little tip here under this one. It brings them together. It creates that concave shape and gives us our 3-dimensional solid, okay? But right now, we're just adding up those angles, all right? So when 4 triangles meet at a vertex, that's 4 triangles, 60 degrees each, that's 240 degrees. When 5 triangles meet at 60 degrees per triangle, we wind up with an internal angle sum of 300 degrees. Okay, let's calculate all of these boxes until we're done here. So I'm doing 3 squares times 90 degrees, 4 squares times 90 degrees. Okay, now anytime I hit 360 degrees, I'm done calculating, because if you recall in that proof by exhaustion, once our internal angle sum equals or exceeds 360 degrees, we no longer have the potential for a Platonic solid, because at 360 it goes flat, and above 360 it goes concave. All right, that shape kind of folds in on itself after 360 degrees. All right, so yeah, I mean, I could keep calculating out here, but it's still going to be at 360 or above, so it creates a problem for our 3-dimensional figure here. So if I have 3 pentagons at 108 degrees each, multiply that out, I get 324 degrees. I'm pretty close to 360, but I still have a little wiggle room here. But when I bring in 4 pentagons together and I try to lay those out together to create a 3-dimensional figure, I'm doing 4 times 108, which is 432 degrees. That has already exceeded the maximum allowable internal angle sum of 360, so I'm not going to continue calculating. I'm not going to count you off if you keep calculating in your table. Nothing wrong with that. But for efficiency's sake, I'm not going to do it. When three hexagons come together, I'm doing 3 times 120 equals 360. Whoa, 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 whoa. We already reached a problem. My figure's just gone flat. Okay, I cannot have a three-dimensional solid with 360 degrees already there because it just lies on a flat sheet of paper. Okay, it lies flat. It becomes two-dimensional. So the big deal here is that we need to use this table. This is going to be sort of a reference that we use in order to prove, okay, that there can only be 5 Platonic solids. The table is just the first part of that. I typed up an acceptable version going through the proof that there are only 5 Platonic solids. Now, we did another version in class, which is perfectly acceptable and very detailed. I'd say it's more detailed than this. All right, so you are fully welcome to go and use that older version of the work that we did in class. I will accept that on your test and your final, right? But I just want to go in order, read through this, and we can fill in the blanks together here. Okay, so it takes a minimum of 3 edges to create a polygon. Notice that we started with a triangle. That's because that is a 3-sided figure. Then we went to the 4-sided figures, then the 5-sided figures, then the 6-sided figures. And it takes a minimum of 3 polygons meeting at a vertex to create a Platonic solid. Okay, sure. Well, look at the table. First we looked at when 3 solids meet, then when 3 triangles meet, then 4 triangles meet, then 5 triangles meet. And we are going to go through that same process, that exhaustive process, for all of these shapes. So let's go ahead and do that. This is the expanded version of the table that you see here. Some version of this proof needs to be on your test. When 3, 4, and 5 triangles meet at a vertex, the internal angle sum is always, well, we can describe that, is always less than 360 degrees. It was 180. It was 240. It was 300. All of those are less than 360. That's why I'm describing it that way. So it's possible to construct a Platonic solid using those arrangements. In fact, when 3 triangles meet at a vertex, it creates a tetrahedron. Tetrahedron. When 4 triangles meet at a vertex, an octahedron is created. Okay, if you want practice creating these, you can go look at homework 12 and the YouTube videos that go along with that. When 5 triangles meet at a vertex, an icosahedron is created, all of which are Platonic solids. However, when 6 triangles meet at a vertex, 6 times 60, 60 is 360. That's a problem. Okay. However, when 6 triangles meet at a vertex, the internal angle sum is 360 degrees, which causes the shape to go flat or to flatten, okay, or to become two-dimensional. This arrangement of triangles cannot create a Platonic solid. We've gone through all the possible triangles, okay? We stop here. We've gone through all the possible triangle configurations that could ever seek to make a Platonic solid. So we move into the squares. This is the next polygon, right? We finished all the triangles, so now we move up to 4-sided figures. Those are the squares. And we must start with 3. It takes 3 polygons coming together to create a Platonic solid. So when 3 squares meet at a vertex, the internal angle sum from your table was 270, which is less than 360 degrees. So it's possible to construct a Platonic solid using that arrangement of squares. In fact, when 3 squares meet at a vertex, a hexahedron, all right, it's a 6-sided 3-dimensional figure. It is also called a cube, is constructed which is a Platonic solid. However, when 4 squares meet at a vertex, the internal angle sum, 4 times 90 equals 360. That's where I'm getting this number from. The internal angle sum is 360 degrees, which causes the shape to flatten, or to go flat, or to become two-dimensional. This arrangement of squares cannot create a Platonic solid because it has flattened out. We finished all the triangles, we finished all the configurations of squares, therefore we move to the 5-sided figure, the regular pentagon. All right, that's the next paragraph here. Let's swap out colors. When 3 pentagons come together, 3 is the minimum number that can come together, the internal angle sum is 3 times 108, which equals 324. Okay, the internal angle sum is 324 degrees, which is still magically less than 360 degrees. So it's possible to construct a Platonic solid using that arrangement of pentagons. In fact, when 3 pentagons meet at a vertex, a dodecahedron, 12-sided three-dimensional figure, is constructed, which is a Platonic solid. However, when 4 pentagons meet at a vertex, that would be 4 times 108, which in our table is grayed out as being 432 degrees. The internal angle sum is 432 degrees, which causes the shape to go concave. Okay, it folds in on itself. Instead of bowling outward, it bowls inward into itself. Okay, it bowls inward into itself, goes concave. It causes the shape to, instead of go concave, you could say fold in on itself. You could say go beyond flat, something like that. Okay, these are just some words you could use to describe this phenomenon. That cannot possibly create a Platonic solid by definition. Okay, so we abandon the idea that 4 or more pentagons could come together, and we move on to the 6-sided shape. What we're trying to do is reach a point where we can no longer construct Platonic solids from even 3 of these regular polygons coming together. Hexagons, that's where it happens. When even just 3 hexagons come together, the internal angle sum is 360 degrees. That math here, 3 hexagons is 3 times 120 degrees, which is 360. Notice that's grayed out in the table already, all right? So the internal angle sum is too high. This angle sum does not allow for a 3D shape. It goes flat. Therefore, this arrangement cannot possibly create a Platonic solid. So no hexagons or polygons with more than 6 sides can be used to make Platonic solids in any configuration because the internal angle sum would be too high. Therefore, there can only be 5 Platonic solids, which we've listed throughout this proof. We listed them here: tetrahedron, octahedron, hexahedron or cube, dodecahedron. Okay, whoops, and I left one out, the icosahedron. So you can list those here, 2, 3, 4, 5. Okay, it's your job to type those up again to be thorough. I'm not going to do this proof that the square root of 5 is irrational in this video, but you can log in. I mean, there's a direct copy of it. It's very easy to find. Log into Blackboard, go to our class, all right, click on the content folder in the left-hand side of the classroom page, which is like a little blue menu. Click content, and inside there, there is a proof that the square root of 2 is irrational. I think it's the square root of 2. It's some square root of some prime number. Okay, and it says minimal wording. Minimal wording, that's what you're looking for. That's the one. That's the easiest one you can possibly do. Okay, so go find that, and that'll be exactly the proof that you're looking for here. So that was the entire test review. At this point, you can go into Blackboard, into the content folder, scroll towards the bottom, and you should see a link for something called Test 2, and I believe it has the due date, which is Monday, April 20th, and it needs to be turned in before midnight that day, so by 11:59 p.m. If you have any questions, please consult your notes first, a tutor second, and me third. All right, I've given quite a bit of leeway on how to approach these problems and how to find your answers, so use me as a last resort. I wish you the best of luck. Yeah, good luck on your test.